Do your kids watch Cat Noir and Ladybug?
It's been a while. My Valence loved them when she was like 4.
You know how I forget what it's called, the little thing for Cat Noir, he likes the cheese in the little triangles. And so whenever I get one of those pieces, that's always what I think of, is like him loving the smell of it.
I can see that. That was that was a phase that that Bill went through for a while. She loved that.
It's a cute show.
I didn't mind it.
Better than K-pop demons. Hardly made you watch that.
No, they haven't even really showed much interest in it, which is weird, but they're both kind of nonconformists, so.
I haven't seen it, but the girls that I coached came in one day and they were like nonstop talking about it.
I was really bored over summer here, so.
Actually, they did see it once. They saw it over the summer when we went to visit my wife's family. My niece is a year older than Dash, and she was obsessed and made them watch it. And they're like, okay, it's kind of catchy, I guess, but like haven't asked to watch it again since or anything.
Yeah. Maybe it's a specific age group that likes it.
It was good. I was really bored over summer, so like I was working here. I was the only one. I can't see any window from my desk. Like it's so boring. So I watched it like twice, and I was like, "Oh, it's so good." And now that I haven't seen it, I was like, "Yeah, I think I was hyped."
I don't miss it.
That was crazy boring.
The series that I did encourage Valence to get really into, and all of my kids have gotten really into, was She-Ra.
Oh, yeah.
They loved that, and I loved.
But are you watching like the new version, or like did you
the new version?
Okay.
Our parents had us watch the old one when we were kids.
The old one's good too, but
that one was good.
it definitely hasn't necessarily aged that well.
Yeah.
But it was definitely entertaining.
You should get them into like Star Wars. Right.
It's too much Star Wars now. There's too much.
There's a lot. I just started getting my boyfriend to watch them. Like he wants to watch them. And I have like a ton of the Lego ships. I'm like, my dad told me Legos wasn't decorations. And he said, we can totally decorate the house. We should totally decorate the house with your Lego ships. And I was like, you want to decorate the house with my Star Wars Lego ships.
I don't have, yeah, that's
how you know it's meant to be.
Right? And like I got him to watch all the movies and he asks me these questions. I'm like, you have to watch the Clone Wars to make this work.
Make this work.
And that's where I got hung up, because there's so much Clone Wars and it takes so long to get through.
Like skip through some of the filler episodes.
I liked Bad Batch though. Watched Bad Batch.
That was really good.
But we haven't watched a lot of the series. The only series we've watched was Mandalorian.
I mean, Clone Wars, I would say there's like definitely all of season 7.
We're on the topic now,
6, and like you can skip through the important episodes in the rest of the seasons if you don't want to rewatch it.
I'll have to find a playlist or a watch list. Like,
make one.
Okay. We'll make a discussion board on Canvas and we can put everything in there.
Perfect.
All right, let's try drawing a Newman projection. Here's a molecule. This is a chiral molecule. Looks just like the one we drew over here, right? Except with bromines instead of OHs. What does it look like if you put your eye in the plane of the board and looked at it between these two carbons? So those are going to be the two that are in the circle. And so you take it, twist it so that your eye is looking. So if carbon 2 is my thumb and carbon 3 is my pinky, twisting it like that. So there's my thumb pointing at us now. And that carbon 2 has a bromine up and to the right, also slightly coming towards us, but we're going to pretend like it's mostly planar from that angle. A methyl straight down, and a hydrogen up and to the left, because the fourth bond attached to that carbon is a hydrogen, right? So then what is the other carbon going to look like?
The bromine's gonna be on the opposite side.
So the bromine is going to be down and to the right.
Okay. Why?
Because this one, so both bromines are sticking out towards us right now, right?
Oh,
So if you put your head in the plane of the board, if both bromines are sticking out, they're both over here relative to the rest of the molecules. They're both gonna be towards the right. This one is gonna be down into the right.
or
It also has a methyl and also has a hydrogen attached. Where does the methyl go? Where does the hydrogen go?
the methyl goes up
Methyl goes up.
and hydrogen goes left down.
All right,
But
Let's-
why are we changing how we look at things?
because they're three-dimensional objects. They're not two-dimensional objects. We're drawing it as 2D, but we're trying to,
Like, why
Just-
do we keep looking at it with the wedges and the dashes?
because I'm glad you asked.
They wanna make life hard?
Because these three-dimensional objects have certain shapes that are favored according to the energy because of the way that they're arranged. Right, so when we look at a Newman projection, we usually draw it in what's called the staggered configuration, where everything is sort of alternating and it's got and they call that the dihedral angle. Basically, the angle of the rotation is about 60 degrees. So you put the three objects in the front are roughly 120 from each other. And the three from the back are 120 from each other, but you arrange them. Like, that was poorly done. So that you put the things in the back in the empty space from the things in the front. And that kind of makes a lot of sense just from a design point of view, because we want to be able to see everything, right? But it also makes sense from an energy point of view. Because these things aren't going to be pushing into each other as much if they're staggered. When they're in the eclipsed configuration, we usually don't draw them so that they're 100% eclipsed, because you can't draw two hydrogens on top of each other and still see them. But what we're representing with this configuration is that these two hydrogens are on top of each other, basically. So that would, or the other way of saying is the dihedral angle is 0. The angle between these, instead of being 60 degrees, is 0. So why does that matter? Why are we looking at these Newman projections? Because these different configurations have different energies associated with them. And if I,
That makes sense though, because I thought they pushed other ones away from each other, that's why they have angles.
correct. So if we just took ethane. So here is ethane as a Newman projection. So
Yeah, for later for me.
here's the staggered configuration.
What happened to not drawing H's?
In this case, we want to show them. Because because this diagram makes more sense if we can see what's attached to the carbons.
So it seems like we're making smaller things more complicated, because we're adding the H's back in and we're putting them all in weird. Why?
Because if you want to
It's
really,
easy. Why, Sean?
all right, let me put it to you in equestrian terms.
Hey, you
I don't know much about show jumping.
Huh?
If I saw somebody ride a horse and they jumped and all 4 feet from the horse left the ground at the same time, I'd say that looks like a great jump. That's not how it works though, right? Because when the more you know about a subject, the more you've got to zoom in on it, the more the small details matter.
So are we just learning this so we can apply it to bigger ones eventually?
It's exactly what we're doing.
Like learning a course with the poles on the ground and then putting the jumps up.
Yeah, there you go.
Right now, we're on the ground.
We're showing why it matters and where everything goes with the hydrogens, and then we're gonna switch the hydrogens out for bromines and methyls, like we did on the last example. Matt,
We're mapping it out.
you don't have to like it, but that's where we're headed.
Exactly like Corey right now. You don't have to like it.
My goodness, you're so happy, jeez.
This is the same tone I have to take with Valence when she tells me, well, I don't like reading. Well, yes, you do, you just don't know it yet.
She
Right.
might be right. I still don't like reading.
I think
That's fair. Not everybody has to like the same things, but you do have to try it.
you gotta know how to do
You
it.
gotta know how to do it.
Like doing the not fun part of silks.
No, it's like mapping a dropout.
It's like doing the weight training that goes along with silks. You don't have to like it, but it's gonna make you better in the long run.
Yeah, the conditioning. But you learn to like it because you gotta do it, and then you know that it gets you to do cooler stuff. So I was thinking about
I just always get yelled at.
Well, I promise not to yell at you.
Well, we're not 100 feet away, so.
All right, so here's ethane. We know what ethane looks like. It's two tetrahedral carbons, right? If you want to build ethane with your models, you certainly could. I'm not gonna stick all of the hydrogens on there. I'm just gonna use empty bonds to represent their space in the interest of time.
So do we use a little one?
Doesn't really matter for the sake of showing this, just know that you're representing a hydrogen.
if it was skeletal structure, it would be just this.
That would be skeletal. So by definition, these are ball and stick model.
Okay.
So ethane looks like this, right? Two tetrahedral carbons.
Wait, what?
They stand up the best if you set them in the eclipsed configuration, right? But that's not actually how they're gonna be the most stable. They're naturally gonna be the most stable when you can rotate them. So they're in the staggered configuration. We can actually measure this. This amount of energy, the amount of energy versus in the eclipsed versus the staggered configuration. When we take this and we rotate it, because remember, these rotate kind of like fan blades. When they rotate, when they pass each other, that creates a small energy barrier. Anytime two hydrogens on adjacent carbons pass each other in an eclipsed configuration, that's about 4 kilojoules per mole of energy.
They push.
They push on each other. So it's sort of like if you turn a dial that clicks, when you turn it, you have to add energy to get it past that click and then it sort of snaps to the next position. That's kind of what's going on here. It's clicking into the next position. You put energy in to get it to the eclipsed configuration. And then when it gets past that, it sort of snaps into the next staggered configuration. And so that makes this sort of sine wavy shape which kind of makes sense because you're doing a rotation. So rotations naturally make us think of sine waves, and if we're trying to map things out in mathematically. What about if it was propane instead of ethane? What if we replaced one of these hydrogens with a methyl group?
So, but this has more energy than this
Correct.
because there's more forces pushing against each other.
Yeah,
If we're stuck in a closet for a day, we're gonna argue more than when we're stuck in a bedroom for a day. You know what I mean? So this, they're stuck in a closet. They wanna go get away.
and so that's that term that I ended lecture a week ago now, where I said sterics. That term sterics basically just means that clouds of electrons push on other electrons and push them away from each other. And the bigger an object is, the more it's gonna push away on other things.
I just said clouds of electrons push on others.
Push on other clouds, I thought.
But considering everything has clouds of electrons around it, really all of these objects are gonna push on other things. It's all just a matter of how big are they and how close are they. The bigger they are, the closer they are, the more they're gonna push each other away. I like to use people sitting in an airline seats as an example. If you put three hydrogens, it's like putting 3 10-year-olds in airplane seats. They might push against each other a little bit, but really they're not really infringing on each other's space that much, right? If you put 3 WWE wrestlers in the same airline seats,
Right.
there's a lot more force against each other just because they take up more space.
Yeah.
So with that in mind, if we did tried to make the same graph for propane instead of ethane, would the barrier be larger or smaller?
Larger,
Why?
because there's gonna be more push with the 3 lined up.
We took one of our 10-year-olds and replaced it with not a WD, an adult. Call it methyl an adult. It's kind of an average size thing. All of a sudden, when we twist it around, the methyl pushing on a hydrogen is gonna be a bigger interaction than a hydrogen pushing against a hydrogen.
So then it would have even more energy. Like this.
It would make this barrier, this gap between eclipsed and staggered would be even larger. Right? What if we did it with butane? Now we have, if we're considering the carbon 2 to carbon 3, now we have 2 big groups or 1 big group and 2 little groups on each carbon. Now when we twist it against each other, a carbon passing a hydrogen gives a barrier. The carbon passing the other carbon is an even larger barrier.
So then this whole thing would kind of bend.
Exactly, the whole thing kind of bends a little bit and makes it less stable. Because you're taking these 2 big things and making them push by each other. Airplanes are my go-to example of places where there's not enough space for the amount of movement that needs to happen. So another example of the rotation would be like, okay, when it's a methyl passing by a hydrogen that's trying to get by a 10-year-old in the aisle versus trying to get by another adult in the aisle. It's gonna be a lot harder versus if we took one of these and we replaced it and we put a bromine there, there's our WE wrestler. So a WWE wrestler past a hydrogen, past a 10-year-old can still happen.
Right.
An adult past a WWE wrestler is gonna be a lot harder even.
Yeah.
Right, so basically it's a sliding scale where the bigger the objects get, the bigger this barrier gets and the more it matters. Because this barrier, so we had a total of 12 kilojoules per mole for it to rotate when it was just ethane. A reasonable barrier that you can expect to happen fairly quickly, a reasonable reaction barrier at room temperature, anything that's under about 100 kilojoules per mole happens pretty quickly at room temperature.
We have to know these numbers.
They'll become important. You don't need to, we're not gonna do calculations with them though. So basically just use that, like, if it's a barrier that's larger than 100 kilojoules per mole, it's not gonna really happen quickly at room temperature. If it's below 100 kilojoules per mole at room temperature, it's gonna get to equilibrium pretty quickly.
So it'll rotate at room temperature.
So it'll rotate at room temperature. So basically, we have this whole thing spinning constantly.
Which is the things we threw the other week, the different formations.
The different conformers, yeah. So that's the reason why all those different conformers are equally valid is because they're all constantly happening. Especially in a case like this where it's only a 12 kilojoule per mole barrier. Basically, this is spinning so quickly, it's like a fan blade almost. It's still gonna slow down when you hit that eclipsed configuration for a second, but then it speeds up and it's got enough kinetic energy that it's constantly doing that. If we look at butane, again, butane's gonna have a more complicated looking function though. Right? So it's not gonna look just like a sine wave. It's gonna actually look more like two sine waves on top of each other because you're gonna have, when a carbon goes past a hydrogen, that gives you a barrier that's gonna be larger than 12 kilojoules per mole. But when a carbon goes past another carbon, it's gonna be even larger than that. So the Newman projection for this conformer would be if we're looking at it like this.
There's only 3 carbons. Yeah, he said. Oh, no, there's a 4th one.
There's a 4th one. So when it's in this shape, in this configuration, and we're looking at it along those lines. There's our, we'll color code things too. So our red carbon is gonna have hydrogen up and to the left, hydrogen up and to the right, and methyl straight down.
And then the back is always the circle.
In the back one is what's behind the circle. So basically, if I was, I'll use a dotted blue line to represent the blue carbon. It would be, it's behind the red one. The red one is in front of it.
The circle's a carbon?
The circle is a carbon.
That's how you know that there's.
I thought it was just a bar.
We still draw the bonds as line. We're representing the carbon as just a circle that's kind of like a sphere taking up space.
Yeah.
So then with the blue circle, does your line come from the blue circle or the red circle?
So that's where the other 3 lines, so the 3 red lines are what are attached to this front carbon. I'm gonna switch colors here for the sake of showing what's attached to the back carbon. The back carbon also has 3 things attached to it. And if we're standing here looking in the plane of the board down that line. So I built my molecule to look just like that, right? So if we take it and we're looking this direction, so if you take it and look that direction, the red carbon is the one that's in front. So you got your hydrogen up to the left, hydrogen up to the right, methyl straight down. So what's attached to the back carbon?
Another methyl and 2 hydrogens, but the methyl's in the bottom right.
Methyl's in the bottom right, good. And then a hydrogen straight up and a hydrogen to the left.
In this drawing one with the dotted blue, wouldn't the lines come from that one?
Yes. So if I was trying to that help?
Because like in reality, the dotted blue is the same line as the red.
Yes. Well, from
Cause
the
they
viewpoint.
overlap, so from that viewpoint, like it's directly behind it.
Correct. So the way that I would draw this if I didn't have color coding, I was just drawing it in black and white. You draw the circle that represents the front carbon. And you draw the things attached to the front carbon. With the lines going all the way to the middle. To show that that's in the front. And the lines that don't go all the way to the middle. If the lines don't go all the way to the middle, that's representing them being attached to the back carbon.
So do we have our midterm next Thursday?
That's the plan. Based on whatever we get through between now and then.
We bring these.
No, but we can paint our fingernails different colors.
My hand don't work like that.
We'll talk about that next Tuesday when we do our review. I don't believe I generally allow that. I have to think about that, whether or not we've done that in the past.
You might be able to get an exception possibly through SAS. It's just gonna be me and you in here, Sean.
It's true. So we don't actually have to take it in here. We can, but we can
Okay.
take it, if you're more comfortable somewhere else on campus, we can. You go take it in the reading room in the library if you'd rather, or something like that.
I'm fine in here, but
Okay,
if we need to move, that's fine with me too.
we'll get more details as we get closer.
Yeah.
So. Is this one going to be the most stable version?
Yes. No, but it's gonna be the most energetic, no.
No.
So what's gonna be the most stable way we can arrange this?
The metal needs to go where the top, yeah.
Okay,
But
So-
that's also gonna be the least amount of energy.
exactly. So most stable means least amount of energy. We use those terms pretty interchangeably. Because that's just kind of the way the universe works, is things tend towards lower energy states. So. And this is not tricky necessarily. But one of the reasons we need to view these things as three-dimensional objects is so that we can look at this and say, okay, well, how do I put it into its most stable state? When you have the model in front of you, that's easy. I want to put these two carbons as far away as possible, so I'm going to take it and I'm going to twist it around, right? What does that now look like here? We know that this back carbon, let's say we're going to keep the front carbon still. Let's keep the front carbon stable. And we're going to twist the back carbon. In this case, it's not that hard to do because both of these hydrogens are identical to each other. But in some cases where you can tell the difference between these two, you need to be careful that, okay, well, this carbon is rotating up and to the left, is rotating counterclockwise. These hydrogens have to rotate counterclockwise as well. Right? I can't take my thumb and point it towards the wall without bringing my fingers along for the ride. All right, so and one of the ways we can draw that is just with a curved arrow. Curved arrow in this case is not representing electrons moving, it's just representing rotation. Or you could even draw it like that around the bond. We're twisting that bond so that we get Methyl goes up. The hydrogen that was there shifts over to this side. The hydrogen that was here shifts over here. That's gonna be the most stable conformer. Right, and so if we actually look at what that same graph looks like for butane instead of ethane, it's a little bit more complicated because each of these is slightly different in energy,
Yeah,
right? And it's not just 12 kilojoules per mole, it's 16 kilojoules per mole to get from the most stable to the second most stable. And then it's 19 kilojoules per mole for the two carbons to pass by each other. And remember, it was only 12 kilojoules per mole for two hydrogens to pass by each other. Or for all three of those interactions to happen. Right, so two more vocab words to describe the three-dimensional shape. When your largest substituents are opposite from each other, we call that anti. Anti means opposite, right? When they're close to each other but not eclipsed, so they're still staggered in these cases. That's what we call gauche. Either of you ever heard the term gauche before? It's like a very bougie way of saying you tried too hard. You're almost cool, but not quite.
so they're almost,
They're almost eclipsed. They're almost stable,
right,
but they're not quite. Not as cool as they could be because they're trying too hard. It's like the way that people would describe people with new money.
yeah,
They try too hard to show off their money. And so that's referred to as being gauche.
I'm not.
I realized when I was talking with Laura about something last night and I used the term expectorating. I'm like, I learned that from Gaston when I was growing up. From
Yeah, from his song.
his song. And I realized that I collect vocab words like kids collect Pokemon. It's like,
Right.
oh, there's a new vocab word. I
Yeah.
like that. Gauche is your new vocab word for today.
I like it.
All right, so let's look at one that's more complicated.
Okay.
Rotating only the carbon-3 to carbon-4 bond. So there's the bond we're looking at here. What is the lowest energy and the highest energy conformation? And draw them as Newman projections.
So just C3 and C4.
We looking at the whole thing though.
So basically, draw a Newman projection
What's that section?
for just that section. So the reds in the front, the blues in the back.
Okay.
So draw it the way it is now, and then try and rotate it to get the lowest energy state and the highest energy state.
Without the other carbons included?
So just like on the last one,
Like the methyl.
where we said we just treated them like a methyl.
Okay.
So draw the circles for your Newman projection for carbon 3 and 4, and then you're gonna, on carbon 3, the red one, It's got an ethyl group attached and a methyl group and a hydrogen. The second one has got two hydrogens and an ethyl.
So we can say C2H6 for the ethyl.
C2H5. Because one of the bonds is taken up by, yeah. Or do a condensed structure by CH2CH3 if you want, either way. The other abbreviation that gets used is if you write it as capital E lowercase, capital M lowercase e as abbreviation for methyl, capital E lowercase t is your abbreviation for ethyl.
You had the ME in the homework, I think, and I was like, me? What's going on?
It's not a new element, that just is shorthand for methyl and ethyl.
Okay, cool. Good to know.
Yeah.
I drew them eclipse test the first one, is that not right?
So for the first one, we're trying, so this is the way it's currently drawn.
Right.
So I just started by drawing it the way it's currently drawn. If we're trying to find the lowest energy,
Is it not eclipse as it's currently drawn?
it is not. So if you look at the red one, if the red one's tetrahedral, it's gonna look like this, right? And then you've got something attached to the blue one is gonna be going straight down. So when we're looking up at it from this direction. So if this is the way it's currently drawn and we're looking up at it this way between carbon 2 and 3, or 3 and 4. When you look at it that way, you've got the ethyl attached to the red one coming straight up, hydrogen to the left, methyl to the right. On the back one, you've got an ethyl going straight down. So let's see what you have, your
When you
model.
look at it sideways. It's not going straight down.
When you look at it sideways, what else is attached to this, to the blue carbon?
2 hydrogens.
2 hydrogens, and where are they? if two of the bonds are in the plane of the board, the two hydrogens have to be going out of the board and into the board, right? In the same general direction. So if we're standing down here looking up at it, if the ethyl group is going straight down, if the ethyl group is down right here, then the hydrogens are up and to the right and up and to the left. It's okay, this is one of the trickiest things about OChem, is getting to the point where you can see a 2D drawing and picture a 3D molecule. Also, one of my favorite little random scientific facts is that they actually did a study about probably 15 years ago now, where they showed that people that play video games do better in OChem classes.
Because it's a 2D screen.
Because you're used to looking at a 2D screen and seeing something in 3D. You have more practice, your brain has more practice with that. It's really hard to get used to that, so that's why we have the models out. Speaking of which, before I forget, Taylor, Riley, I dropped a carbon and it bounced off my shoe and it's right underneath your bag. Oh, now it's underneath your right foot.
Okay,
Thank you.
yes.
All right, so this is the way the model is currently. Is there a lower energy conformation? What do we want to minimize to get the lowest energy state?
Lower energy be eclipsed.
So low, if it's eclipsed, that would be putting these ones on top of each other, right?
Well, but then you
Also-
could separate the methyl and the carbons.
We've got a methyl here. It's gonna try, the methyl's gonna naturally try to be further away from from the blue ones, right? The methyl can't get any further away from the red ethyl because they're attached to the same carbon. They're already stuck next to each other. We could get the methyl further away from the blue ethyl group though, right? If we took the red carbon and rotated the whole thing.
Yeah, but then wouldn't it wanna be the blue carbon, wouldn't it want to be in the middle of the two red carbons? Instead of, so then it would wanna be directly behind a hydrogen.
So that's exactly, you've got the right logic, but you're going the wrong way with it. To be the lowest energy state, we want all of our big groups as far away from each other as possible. What you described is the highest energy state, is putting them close to each other. So right logic, wrong direction.
I didn't put them close to each other, I put them evenly spaced apart, it just happened to be behind a hydrogen.
But if
So,
you're behind a hydrogen.
But if it's
super
eclipsed, if we rotated it so that this carbon was opposite from these two, then that means that would be putting us in at the top of one of these. So the most stable state is never going to be eclipsed. Because if it's eclipsed, we're sitting at the top. So, and one of the ways to think about energy is it's like elevation. We're used to going through passes up here, right?
Okay, so stable isn't eclipsed?
Stable is always going to be staggered. Stable is at the bottom of these. It's more if you took a bowling ball and you took it to this top of Spooner Summit and you put it squarely at the top, which is it going to stay there? No, it's going to roll. Which way it rolls is going to be kind of random, but it's not going to stay. You can't put a state right at the top here because it's either going to roll that way or it's going to roll that way. Things naturally collect at lower energy states. If we took a box of 1,000 ping pong balls and we took it to the top we'll use Kingsbury because it's steeper, it's more fun. You took a box of 1,000 ping pong balls to the top of Kingsbury and you dumped it out right at the summit. Half of them are gonna go towards Minden, half of them are gonna go towards Tahoe, right? None of them are gonna stay there though. Because at the top, a local maximum is never a stable state.
So then to stabilize it, it's whoever wants to be farthest from the
Bingo.
big one.
So you take your biggest groups, and you,
That is stable.
this is the most stable state,
So the original one is the most stable.
correct? Good job. What's the lowest energy? Or sorry, what's the highest energy? What's the least stable?
Blue one behind the red hydrogen.
That is one unstable state. The most unstable would be putting your biggest groups on top of each other instead of being opposite from each other, right? So if we rotated the red carbon 180 degrees, our least stable state would look like this. So to do that, I would have to take this front one and you rotating it 180 degrees, then puts the methyl that was down and to the right is now this direction. And the hydrogen that was down and to the left is here. So we took this state and to put the two ethyls on top of each other, we did that. And now when we look at that from carbon 3 to carbon 4, I didn't draw that right. I should have drawn these all the way in. We get something that looks like this. The two methyls straight down, two hydrogens up and to the right on top of each other. Hydrogen up on the blue carbon is up and to the left, and the methyl is up and to the left. So having the 3D model was really helpful for that, right? Especially while we get used to it. It gets a lot easier once you get used to the rules of, oh, I know I can just take all three of my red things and rotate them wherever I want. But going from skeletal structure to the Newman projection and then rotating it, this is exactly what you were asking about earlier, right? Why are we doing this? Because not all of these different ways of arranging it are equally stable.
Well, you can't do this for everyone because not everyone has the stable bonds. Once you get to pi bonds, you can't.
I'm glad you brought that up. Because it turns out ring structures also have that problem, right?
Yeah.
Because they're already locked into a configuration. So I think we're good for today. We'll end lecture a couple minutes early. And we're gonna talk about ring structures and substituted rings on Thursday. Right, and so bring your models again on Thursday. And we're basically gonna use spend all day on Thursday talking about cyclohexane and the different ways it can rearrange itself.
Okay.